Okay, let's get started, please. I have a ton of just logistical announcement stuff to cover with you guys to get started today. First off, I've been grading like a madman to get caught up with all that stuff. So the good news is Lab 1 is done. Your grades should be on Blackboard unless you used a late coupon. I haven't gotten to those yet. Turned it in on time. Your Lab 1 grade should be on Blackboard. I did not bring those with me today. But if you want to pick up your Lab 1 or any of the completed assignments, you should swing by my office hours. I'm having office hours tomorrow from 1 to 4 and on Thursday from 1 to 4, I believe, as well. So swing by and pick up your homework assignments if you want. What else? The exams are very, very nearly graded. I've got about 50-ish of them finished. And the ones that are left, I only have one problem left on them. So those will be back on Thursday, absolutely positively back on Thursday. So far, everything's been great. It looks like the average is going to be in the high B range, so I'm pretty pleased with that. That's a good place for the average to be. But we'll talk more about that on Thursday. Homework assignment 2 is also almost finished, and I really, really hope that I can get that back to you on Thursday. That kind of depends on my TAs. So I'm hoping we can get all caught up on that stuff this week. Also, I posted the next lab assignment. So the next lab assignment is on the course website. I posted an announcement to Piazza about that earlier today. We will spend some time talking about that towards the end of class today. I'll save 10-15 minutes at the end to kind of go over the specification with you to make sure everybody is on the same page as far as the lab goes. You are allowed to work with a partner, just like you were with the last lab. We'll talk more about that at the end of class. Are there any questions about stuff that's coming up? All right, fantastic. So today we're going to start in on section 2, basically, of the material. Everything we've done up until this point, of course, is still going to be extremely useful to us. So, don't forget all that stuff yet. Wait at least until the end of the semester because we are going to need it. So today we're going to talk about latches and flip-flops and some registers as well. Let's start off with just a couple of discussion questions about some of these things. Who can describe to me the difference between a latch and a flip-flop? What's the difference? There are several, actually, differences that are set as an answer to this question. Yeah?
Well, flip-flops depend on the clock.
Depending on the clock, whereas the latch is dependent on the input. I can hook a latch up to a clock if I want to. In fact, that's not a terribly uncommon thing to do. So I think I know what you're trying to say, but just to word it slightly differently. Yeah. Right. A flip-flop only stores on the rising edge of the clock. So if I have a clock signal that looks something like this, which is a signal that we are going to be seeing, a lot of for the rest of the semester, right? A flip-flop can only store stuff on the rising edge, right? How does that contrast to the latch? How is that different from what a latch does? Yeah. Right, so whenever enable is high, which if we're using clock as our enable, which is not an unusual thing to do, right? That would be this entire scheme, right? That would be this entire piece of the wave. Why do we do that? Why is that such an important difference? What's the big deal? Seems like a minor thing, but it's very important. Yeah. Exactly. Right. Is it easier to synchronize things when I've got this giant gap of time in which something might be happening, or is it easier to synchronize things when I've got a very short sliver of time in which things can be changing? Right. The answer is, the shorter amount of synchronization time I have, the easier it's going to be for me to actually synchronize all of those particular components. So latches are great, right? Latches are extremely useful, but flip-flops are easier for our synchronization purposes. Because we're going to be talking about synchronous circuits, that's going to become a very important concept over the next few weeks. Right? Any other differences between latches and flip-flops? There's some easy ones. Easy differences. How many gates? Which one can have more gates? Flip-flop, right? It's going to have way more gates than a latch. Why is that? What's a flip-flop made out of? It's made out of latches, right? So flip-flops contain latches, right? So that's another important concept to keep in mind. What's the difference between a flip-flop and a register? Yeah. Yep. Tied together, yes. So they're all in the same proximal. Exactly. So you could actually make the argument that a flip-flop is a register if you wanted to. It's just a one-bit register, right? Typically, we think of registers as being multiple bits, so a whole bunch of bits strung together. That's more useful for us to talk about for lots of purposes, right? So we use lots of flip-flops to represent a register. Fantastic. What's metastability? You can describe this concept of metastability for me. You already got one today. Appreciate it, though. Anybody else? Yeah. Stays constant and isn't changing. Okay. Anybody have another definition for us? Yeah. It's when it's always changing. It's when it's oscillating, right? It's when it doesn't stabilize. That's metastability. So it's not stable. It's constantly oscillating. And for an SR latch, you're right. It's when we provide the inputs to be 1, 1. For different latches, though, different input configurations are going to lead to that condition. So there are other latches in the world besides SR latches. It's just the one that we care the most about. And it does have this metastable state. How do we avoid it? How do we get rid of metastability? What do we do? Yeah. D-latch instead of an SR latch. Yeah, what's the difference?
The D-latch never lets it be in state where SR.
Yeah, so it just eliminates that possibility from ever happening. I believe it uses just a few additional gates to make that work, right? We'll talk about that a little bit more later on today. Yeah, and so that's kind of the answer to the last question, right? Between SR latch and D-latch. Cool. Any other kinds of high-level questions before we dig into some more detailed examples on latches and flip-flops? Fantastic. Well, these I'm going to leave up to you to try to do, right? So we talked about this before the previous exam. Most digital circuits rely only on NAND gates. So the diagrams that were shown to you in the textbook and on the video did not use NAND gates at all. I don't think there was a single NAND gate in any of those, right? So your task is to redraw an SR latch and a D latch, right? Using only NAND gates. That's it. Maybe an inverter or two if you really want to, but primarily NAND gates. So take a few minutes see if you can figure that one out. And then instead of using D latches to construct a flip-flop, I want you to construct a flip-flop using SR latches, and then be able to tell me what the differences would be between those two particular configurations. So take 10 minutes or so. Talk to your neighbors. We'll be around if you have questions, and then we'll talk about the answers. How's it going, man?
Good, how are you?
Good. How late did you stay on Saturday?
Like 4:30.
So not long after I left. I think I left around 4.
Yeah, not too long.
Yeah. I don't know. I've been blowing through those remaining ones. So.
Okay, good.
I'm
Yeah, we
not
thought you
quite,
would.
Not quite done yet, but I'll be done probably tomorrow. Yeah. I'm using it burger. And I guess another thing I should point out is that the truth table doesn't have to be exactly the same. Yeah, I want to be able to store. I want to be able to store a bit, right? I want to be able to.
Yeah, we have the exact same thing. Like he was on the opposite side. Mine on the. Oh yeah.
Somebody want to come up and draw their SR latch on the board for me? Anybody come and draw that SR latch? I mean, anybody? Okay, let's talk about these problems. Who can help me out with this first one? How many NAND gates do I need to get this done? How many do I need? Yeah. 8. Can I get any lower bidders? Yeah. 6. Any lower bidders? 4. I hear 4. 4. Going once. Going twice. You could say 3, but then you might be wrong. 4 NAND gates. I actually would posit that you could do it perhaps with hang on a second, how many would I use? Probably 2. I think you use.
Are you counting your knots?
Yeah, you kind of
I don't think you need the knots, actually. So, let's just take a look. Right, so I need these cross-coupled guys, right? Here's my outputs, and you probably have your knots over here, I'm guessing. Is that right? You have inverters over here. So if you did that, that's not necessarily wrong. So the question was a little bit ambiguous, and I will admit that it was perhaps intentionally so. I didn't say the truth table had to be exactly the same. They had to be exactly the same, right? So if I posit this as my SR latch, right? Choose S, choose R, I don't care which one. Which doesn't really matter to me. How does this work? How does this work? Is it pretty close to the same behavior that I would expect from the SR Latches ABC? What do you think? So S goes high, what happens? This gate will be on or off? Do we know? Yes? No? Off, right? S is high, I know this will be off, right? So I've got a 0 coming in through here, and if reset is also low, this will be 1, right? So I'll have a 1 here, and a 0 here, which means I've successfully set if this is my Q, right? Okay, let's consider the other case when S is 0 and R is 1, right? If S is 0, if R is 1, I know this guy is off, right? This guy is going to be on, so I see 1 and 0. So set and reset work exactly the same. Everybody see that? Yes? I did not make that assumption. I asked you guys whether it was going to be on or off, or whether we didn't have enough information. Somebody said off, so I ran with it. Right?
Yeah, we don't know.
Yeah, I perhaps would agree with that assumption. It's currently
Shorting here.
yeah.
How exactly did you get that simplified? So,
I'm sorry?
how did you get that simplified? So,
Well, so the question then becomes, how do I store a bit? Right? How do I actually store a bit in this configuration? Does 0, 0 store a bit? That's what I did in our original one, right? 0, 0 stored a bit. So what happens, let's assume we're in this case right now, where this Q is 0 and the other one is 1. And then what happens when I go to 0, 0? So these both go to 0, right? If I move this over, I've got 0 coming in here, so that's going to be a 1, right? And then I've got a, let's see, I've got a 1 coming in here, so that's going to be 0. Looks like, I'm sorry, you're absolutely correct. 1, 0 is 1. I misspoke. Thank you very much. 1, 0 is 1. So we were talking about not and. So then what happens? This becomes 1, right? This becomes 1, which means that's now 1. And wait a second, what happened? Something doesn't feel quite right here. We ended up in a, hang on, let me start over from scratch. I screwed something up. My fault. Let's just redo this from the beginning. All right, we're going to say that S is high and R is low, right? So let's do this one first. This one is 1, this one is 0, right? So which one of these do I actually know the result of? I know the result of the top one is 0, right? Okay, cool. So this is now 0, and now I know the result of this one is 1, right? Perfect. So we get our set. This is 1, which actually conforms with what we saw before. Now I switch S to go back down to 0. Right? I switch S to go to 0. What happens? What happens? This is now 0. 0 and 1 on a NAND gate is 1. Right?
How did you originally, when you had S0, decide that you
I'm sorry? How did I originally say what?
never mind.
So NAND gate truth table, right? It's just the opposite of an AND, so it's going to be 1, 1, 1, 0.
Yeah, so the other group was high.
So if I see a 0, I know the output's high, right? If I see a
Yeah.
0, I know the output's high. When they're both high, then that's 0.
Yeah.
Right? What happened? Okay. And so what we actually end up with in this particular case is a situation where I've got both of, so this now becomes 1, but that actually doesn't affect anything, right? Did it store our bit? Yeah, it did, kind of, but it changed the output of this guy, which, if you remember from our discussion, we always want these two to be opposite. That's preferable to us, the operation of our circuit. What happens if these are both high? What happens if these are both 1? Doesn't give us metastability. That's sort of another question that's worth talking about. Do we still have metastability in this? Yeah, is there a question in the back?
yeah.
Yeah. When S is 1 and R was 0, right? This is what we start out. I actually asked for questions from the audience, and I did receive that this would in fact be 0, but if that's not actually the case,
Received that would be 1.
I received that this would be 1, which is actually true, but we can't actually define that for certain until we see this 0 down here, which defines this is actually, that's not true, right? 0. I see a 0 here. I know automatically this is a 1. 1 and 1 NAND 1 going in here is 0. So this is the correct configuration when S is high and R is 0, right? And so then we saw that when S goes low, we now have the situation where this guy flips to be a 1, and then that's it, basically, right? Nothing else changes. So then what happens if they both go high? Let's say as an alternative scenario, what happens when this guy goes high? What do we get instead? So in this particular case, R is now high. I've got a 0 and a 1 coming in here, and what happens? Nothing happens. Do the outputs change at all? The outputs actually don't change at all. So is that a good thing, bad thing, indifference? Do we care? Do we not care? So what do we notice? Assuming I don't care about this output, assuming I can ignore that second output, which isn't actually used particularly often anyway, what do I have now? I have the case where if I go to 0, 0, or 1, 1, or set and reset, it's going to store the bit in either particular case, and I'm avoiding metastability altogether. Right? No longer have metastability in this circuit, which seems like a good thing to me. Seems like an advantage. Seems like a nice thing to be able to do. If you put the inverters in, then I believe you get similar behavior to what we saw with our original circuit, which is also not a bad thing. Right? We just need to be careful about disability. You want to avoid that case. Yes? So, it needs to store a bit, a single bit, right? And it needs to be able to do both of them. I can't just store a 1. You need to be able to store a 1 or store a 0. You need to be able to store either. Make it happen. Right? So, maybe a little bit deceptive here. This does not behave exactly the same way, but it does store bits. Right? We would argue that, yes, it does in fact store our bits. It stores information for us based on the previous configuration, which is what a latch is supposed to do. Right? Okay, so then if you wanted to turn something into a D-latch then, right, what would that look like using NAND gates? You can assume your inverters are here if you want to, that's fine with me. Right? Regardless, how do I turn something into a D-latch with NAND gates? What do I need to do? My circuit. Make it that far? Yeah.
You need to take your current circuit that you have there,
Yep.
and instead of S and R, those would be the outputs of 2 NAND gates.
The outputs of 2 NAND gates. So you're saying I need 2 more NAND gates in here?
Yeah.
Okay. And then
And then you have your E.
I have my enable bit.
Yeah, your enable, which gets put into each
Both of these guys, okay?
And then you have your D.
Then I have my D.
Which one goes into the NAND gate, and then the other one gets knotted and goes into the NAND gate.
So this is actually exactly the same, right, as our D-latch is normally configured, except for what? We're using NAND gates here instead of AND gates. Does it give us the same behavior? Right, that's the question. Let's take a look and make sure, right? If the enable bit is high, does that tell me anything about whether these gates are on or not? Not necessarily. No, it doesn't. Right? However, if they are high, right? If D is a 0, then I know this is a 1. And if D is a 1, I know this is a 0. So it's basically inverting D. If enable is high, I'm getting D inverted in through here. What happens, down here then? Right? I'm getting the actual value for D on this side. So if D is a 1, I would get a 1 out. If D is a 0, I'd get a 0 out in this particular case. So these will always be the opposite of one another. Do you see that? These will always be the opposite, which is exactly what I would expect. If E is 0, what happens then? What do I get instead? Well, I know for a fact that both of these are going to go towards 1, which we just talked about is going to store the result of our previous configuration. Right? So that is going to act as a latch, right? Except for, and actually in the same configuration. If enable is high, I can set the value. If enable is low, then I'm just going to remember whatever the previous value was that I fed into it. Right? Except for now, I might be dealing with D not instead of actually D. But that's an easy thing to work around. Are there any questions about that? This is actually, you know, if I peel open a chip and look at the latches inside of the flip-flops, this is actually what I would expect to see. This very circuit. What I would expect to see. Yes?
So, if the ones that we saw the configuration on the video that had like all the and or things like that, that's not actually what people use to actually do this?
Everything in a circuit is done in NAND gates, right? Everything in a computer chip is done with NAND gates and maybe an inverter or two, but even an inverter is just another NAND gate, right? It's just one more NAND gate. So yes, everything is done with NAND gates. So I think it's good for us to remember that fact and to consider what the NAND gate configurations are. However, for us as humans, it's not always convenient to think of things in NAND gates. It's kind of tedious, right? So we will still use the other gates. Yes? NOR gates and NAND gates use the same number of transistors. Right? So I actually don't know why they chose NAND gates over NOR gates. I mean, it might have just been pulling numbers out of a hat for all I know. There's probably a good reason for it, actually. I just do not know the reason for that. It's a very legitimate question. Conceivably, you could take a circuit and construct it entirely out of NOR gates if you wanted to. Take a computer chip and construct it entirely out of NOR gates if you wanted to. But nobody does that. Everybody uses NAND gates. Potentially. I mean, that's a pretty. I would want to see some proof, right? Citation needed for that one. But yeah, I mean, possibly. You know, seems like a potential explanation. Yeah. I don't know. It's a great question for the Google. Any other questions about this problem? So what if I were to construct a flip-flop out of SR latches instead of D latches? I don't care if you want to think of the NAND version or the not NAND version, the regular version that we saw in the videos. What's the effect? What effect does that have on my latch when I do that? Is it a good thing, a bad thing, a different thing? Think I get that far? Should we draw it up on the board and see for ourselves? Okay. So maybe we can just use our regular NOR version since that was in the videos and such. I just want to take two of those guys and hook them up. So that's 4 NOR gates, right? I don't think I need any more than that. Right? So I need to cross couple these guys, which is, yeah. And then same thing over here. Right, cross couple these guys. And then I've got my inputs, S and R. Is that the right name? I don't know. We'll talk about that, what that actually means. And then, you know, the outputs, I assume, are going to be fed in like this. And then I've got U and not U. I don't know. I mean, it's kind of what I wanted you to figure out, right? What are the implications of this? Did anybody get to construct a truth table and see what happens? Yeah.
So, if you have a D-latch, it's like you mostly just turn the ands into nans. Isn't that making it input all backwards?
Not necessarily. Well, so we talked about how the D, right, the data bit was sort of inverse from what we're used to when talking about D latches, but the enable bit actually worked exactly the same as we had it before. Nothing was changing when enable was low, right? Because those NAND gates were stable. They were effectively shut off. They put the latch into storage mode, right? So the input was just going to be ignored. Well, so the reason that it works, right, is because with an SR latch, we can store on 0, 0, right? With an SR latch made out of NOR gates, we store on 0, 0. With an SR latch made out of NAND gates, we store on 1, 1, right, when our inputs are 1, 1. So yes, we did kind of flip things around, but it remains consistent throughout the circuit. So it all works out. Yeah? One being inverted. You know, I'm actually should have probably looked this up before class. These might be crossed. I can't remember if they're crossed or not. Or are you saying just ignore this one entirely and just use this one? Or just use this straight into this? I'm not sure I understand what you're. Right, but we don't have an enable bit here, right? We have S and R, so it's gonna be different, right? It's gonna be different. I think we already kind of see that that's kind of the case. This is not going to operate the same as our flip flop, and how could it? I don't have an enable bit here. S and R are both combined together in a D flip flop and a D latch. So one input called D, and then we introduce a second input called E for enable. I have no concept of enable here whatsoever. There is none. How could I? Right. All I have is the D part. I don't have the E part. So what does that do? Does that make this circuit any kind of useful or not? Or is there a different configuration than what I've drawn up on the screen that could perhaps make this useful or not? Anybody play around with it and shift on it? I mean, what do I have up here on the board now, right? What happens if we try to use this as a flip-flop? If we keep, you know, set high and reset high, what happens? So I know this would be 1, right, and this would be 0, right? So I see a 0 here and a 1 here. Which of these NOR gates do I know based on this information? Not OR, right? Just a little refresher. It's going to be the inverse of NOR, so it's going to be 1, 0, 0, 0. So if I see a 1 coming into a NOR gate, I know for a fact the output is going to be 0. So I know this is 0. I know that this is also 0. Right? So this is going to be a 1. So unsurprisingly, it just flipped. Just flip them back. Just flip them back to the way that they were. So what is this actually doing? It's just flipping. Every time I put them through here, it gets flipped. Every time I put them back, it gets flipped the opposite direction. And if I try to, you know, store this by putting these both to 0, then what actually happens, I'm going to get, well, I know this will remain stable, and I know that this will also remain stable, right, based on how an SR latch works. So this is not really a flip-flop per se. This is just two latches in series. You just try to create a flip-flop out of them in the same configuration that we use a D-latch for, and it didn't work. It didn't work like this. Did anybody come up with a different configuration? I know you were asking questions about this, right? Do you have an alternate configuration that we could try that perhaps might be more useful? D would be equal to S and clock would be equal to R. So is it drawn like this, but you just are, I'm not sure I understand what you're saying. Uh-huh. So you have an inverter here, and then like this, and then you just ignore this. This is just not connected, or it's just an output, I guess. Disconnect this, and then feed this in, like that. Okay. Let's take a look and see what it does, right? Let's take a look and see how this behaves. So in this particular case, if S is 1, let's say, and R is 0, what happens? Well, R is going to be 1 through this inverter. So I get metastability here. That's not a good start. That's a problem. So maybe that's just not the right input. Maybe we can try something else that'll get us somewhere better. You know, what happens if I'm in 0, 1, like this, right? So if I'm in 0, 1, this will now be 0, so it's just going to store whatever was in there previously, right? Because the input is my SR latch. So 0, 1 now becomes storage in this particular case. What effect does that have down the line is the question. This now becomes a 0, I don't know what this is. It could be a 0 or a 1. Right? We don't know. We can't say for certain whether it's a 0 or a 1. We can't even say what this is for certain. Right? We just don't know. But if this is also a 0, then this is also going to remain stable. If this is a 1, then what happens? If this is a 1, then this becomes a 1, and that becomes a 0. I guess I'm just not sure how I could define this behavior as a flip-flop. Yeah.
Yeah, on the bottom right, it should be equal to
If R is a 1, oh, you're absolutely right. I'm sorry. I wrote it down wrong. Thank you. That changes, yeah, well, it does. It does change things, right? So I've now basically set my reset bit to be high. But that means that if I have a 1 here, I'm back in metastability on this side, which is still not a good thing. If this is a 0, then what do I have? I have a 0 here and 1 here. Right? And I'm going to actually be holding that stable, right? I'm going to be holding this value stable because this cannot change while these inputs are in this particular configuration, which means that these can't change either, right? Can't change at all anymore either. So we did 1, 0, we did 0, 1. What happens if we do 1, 1? Maybe I should be writing these down too. If we do 1, 0, that's metastability. If we do 0, 1, we end up with the equivalent of reset, I guess, but stable. Right? If we do, let's see, 1, 1, this becomes 0, so that effectively becomes, this becomes a 1, right, through our set. This becomes this remains a 1, actually. We end up with metastability in this one, so that's also bad, right? 1, 1 is bad, metastable. What happens if we do, I guess 0, 0 is the last one that we have, right? 0, 0. So I get a 1 here. That's going to put a 0 on this end. I have a 0 up here. That's going to put a 0 down here as well. So 0, 0 is going to store the previous state, whatever that value is. So it's going to store. But the problem is that I can only ever force this output to be 0. I can never force this output to be 1 in this particular configuration, which is a disadvantage. Right? I'll tell you what, I don't want to spend any more time on this problem. There is a configuration that you can put together with 2 SR latches that is perhaps somewhat useful. I want to see if you guys can figure it out. If you don't figure it out, if you do figure it out, let's say, post up on Piazza. If you don't figure it out, ask me on Piazza tomorrow, and I'd be happy to tell you the answer to this particular question. Right? But I do want to see if you can figure it out. Yeah.
The one that you showed us isn't useful because it's not really like.
There's no way to store anything. Well, I mean, it's no different than just a single SR latch, right? It's no different than just a single SR latch together, right? It's just going to be the inverse, basically, of an already existing SR latch. So it doesn't give us anything that we didn't already have, in other words. It doesn't act as a flip-flop, in other words. Yep. I'd like to move on because we are running a little short on time already. So let's try something different. And if you do get a good answer, please post up on Piazza for me. All right. These are flip-flops. I can tell they're flip-flops because of a little arrow here, right? There's a little arrow. So your task now is to construct a truth table for both of these particular configurations. Can you describe what the behavior of these circuits are? These are actually very well-known, famous circuits. Right? So the question is, can you tell me how these circuits behave? Can you construct a truth table for me? Take 5 or so minutes. Shouldn't take you forever. Yeah. It's an input. It's an input called T. Yes. So it could be true or false. Right? So this one has 4 input combinations. This one actually has 8, so I got 3 inputs going on. Don't forget the clock, right? Don't forget to include the clock in there. Usually we care more about the Q, that's just why it's on top. A lot of times we don't even use Q not, although you can see that we are using Q not in this particular case. Most of the time we won't use Q not, we don't care about it, but this time we do. Yeah. This is the, in fact, I think I showed you this exact diagram. Yes. It can be represented in multiple ways, right? But sometimes they'll leave Q not off entirely. They just won't even be in there for it. It's always there, but if you don't care about it, then sometimes they'll just leave it off. So don't be thrown off when you see your flip-flop with all the 3 pins. It's an implied inverter, right? Saying that it's the opposite of this. It's not an actual inverter. You shouldn't invert Q naught. That would just confuse. So when you see an inverter on a pin like this on a component, it just means that the output is going to be the inverse of something else. When you see it on like a gate, for example, it's an actual inverter. When you see it on a component, it's usually not an actual inverter. Yes, yes, exactly. Yes. Unfortunately, no. I mean, you kind of have to assume it both ways. Yeah. If you really don't know, then the answer is, well, it depends on the previous state somehow. It depends on the previous value somehow. So, like the very first time it is ever it's undefined, right? It's quite literally undefined. If you do it in a circuit, for example, it will be undefined, and it's actually that you want to, for example, start a flip-flop in storage state. You can just normalize it. We need to reset it or reset it first, and then we can go to the storage state. Yeah, but never storage state. We don't know what we're going to get. I don't know why NAND is used in faster memory. It's interesting. Yeah, because the way that it's wired, you need higher capacitance transistors to make more bits or the same throughput. Higher capacitance, small bits. So, like, the transistors have to be higher capacitance. Yeah, I'm just trying to understand why that would be in that particular case. It must have to do with the fact that the port and pull-on networks are basically reversed for a NAND. Yeah. It must be better to have the PMOS in series, or I guess it'd be PMOS in series.
I think it's because like when you add anything in parallel, it's the prolongation, and so the total capacitance, the total voltage expression that the circuit sees is less when you're adding in parallel.
Yeah.
Like if you need
Yeah,
total impedance of something, you need both of those to be that impedance.
Right. I guess it kind of makes sense. Yeah. Cool. Thanks for looking it up. I did not know that. Or if I did, I forgot it.
At one point, you probably knew.
At one point, I'm sure I probably did.
The box is a yeah.
These are flip-flops. We can tell because of the little notch right here. Whenever you see that notch on the clock, that means it's a flip-flop, not a latch. Eventually, we're not going to see latches anymore at all. So they'll pretty much always be flip-flops. Yeah.
I know what it is. I know what it means. So,
Oh, for the right edge. Yeah, I mean, I suppose. So, I mean, since this is a clock signal here, you can assume that if it's one, that it is coming from zero. Like, it's not going to be stable at one, right? Or maybe, in other words, right? What is, assume this is the rising edge, right? Whenever I say one here, the clock wave. Probably. Yes. Yes.
I mean, the clock is zero. Yeah, so you're in parallel. So it's just going to be the 0, 1 is going to be whatever the key is previously, and then from 1, 0, 1, 1 is going to be whatever or what exactly? Like, because when you go from 0 to 1, T is 0. So Q is 0, and that's there's the source. T is 1, T is 1, source 0. Yeah, source. And then T is 1.
I mean, like I said, I'm not saying that.
Well, when it switches, yeah, we'll just assume that it's always in position. So it's the interest. So if Q is 0, then put 1 to be right?
Yeah.
And then if Q is 1 and Q is 1, we're going to flip Q to 0.
Yeah.
And then if Q is 0 and Q is 0,
because it's across because we're taking the output is
And then Q is 0, Q is 1.
so we're taking
Okay.
Okay, so basically what you're saying is
whatever it is. Because I mean, if I do a 0, 0, low, it could be 1 on top, 1 on bottom, or it could be 1 on bottom. It depends on what Q starts at. That's how it's a Q. So if I sell you the 0, 0, 0, and I sell the output, sorry, Q is low and T is low. What if Q started out at 1? Then T is or 0, 1.
Okay. Oh, sorry. Then Q stays.
Right.
If Q is 0, it stays.
Yes.
If Q is high,
No. Just the same constant on the output. Because Q is 1, and Q is 1. It's going to switch to 0.
and then the next time that the clock goes high, you have 1 and 0, which is 1, and you flip Q to 1.
Oh,
Yeah, so T is high.
okay, let's talk about these. So, now I asked you to write out our truth table, right? But the truth table is a little bit misleading because we're dealing with flip-flops here. So what really matters is when the clock goes from low to high, right? So when the clock is actually high, we don't really care. We care about what happens when the clock goes from low to high, right? From low to high. So in some sense, whenever the clock is low here, I know for a fact that whatever Q was before, it's just going to remain that thing, right? It's not going to change. There's no way it could possibly change what it was when the clock is low. So, the output is just going to be Q, right? It's just going to be the same. It's just going to be the same as whatever it was when the clock is low. So that leaves me 2 conditions left on this first one, right? So with these remaining 2, think about the rising edge of these, right? What happens on the rising edge when T is 0 versus when T is 1? What actually happens? Anybody describe it for me? Yeah. Okay. It'll be the opposite of Q. So it's going to flip it, right, to something different. And so this is actually, the name of this is called a toggle flip-flop. Right? If T is high, I toggle it. I just flip it to whatever it was, to the opposite thing of whatever it currently is. Right? If T is low, then it just stays the same. It's called a toggle flip-flop. Does that make sense? Are there any questions about that first one? What about the second one? So again, right, if the clock is low, right, you can just pretty much automatically fill these in. Nothing's going to change. How could it? How could it when the clock is low? And for the rest of these, we need to think about the rising edge, right? What happens on the rising edge for each of these? So did anybody figure out what's going to happen on this J and K circle? Did we figure it out? Or do we need to work through it together? I guess we can just work through it together. Let's take a look. So first case, right, J and K is low. We have this issue here where we're not quite sure what the value of Q is at our initial starting point, which matters because it's getting fed in. Right? In fact, we can see that if the output is 0 in this particular case, right, if the output is 0, this guy will be off, and this guy will be on, which matters. And if the output is 1, then this guy will be off, and this guy will be on. Okay? So we can see already that only one of these is going to be active at any given point in time. So our answer here depends partially on what Q is. Right? It depends on what Q is. So if Q is high in this particular case, and J is low, then I know for a fact that this guy is off. Right? Or I'm sorry, Q is high, right? And we don't care about what J is, so J doesn't matter. We do care about what K is. If K is low, this will also be high, so I get a 1 fed in through here. Right? So no matter what happens, if Q is on, right, I'm going to get a 1 back out. Right? So that's one possible case. So if Q is high, I'm going to get true. How do I write that down?
Just Q, because Q
Yeah.
is how you get through Q.
Right, so if Q is low, then what happens in this particular case? This is off, so it doesn't matter. I just get false. So I just get Q back out. So what happens if we run through the same configuration where K is high? Well, if Q is false, this is still off. We only have to take care of this particular case. If Q is low, then this guy is on, but this is low, so our output's going to be the opposite. So what does that imply then? If,
0, 0, 1.
I'm sorry? I heard too many people talking at once. Yeah.
If Q is low, why would the bottom one be on?
If Q is low,
That would fit.
oh, then this one will be off. I apologize.
Yeah, 0, 1, you get both hands are always off.
Both ends are always off. So what's going to happen?
You get 0.
You get 0 out.
Because you're putting a 0 into the J1 and you're putting a 1 lot into the J1.
Yep. Yep. Exactly. Let's talk about this case here. So with this one, the only one we're talking about is actually both of these could potentially be operational in this case, right? This AND gate could be active. This AND gate could also be active depending on what Q is, right? Depending on what the value of Q is. So if Q is high in this particular case, this one will be on. So I'll get a 1 in through here. If Q is low, right, then this guy will be on. And I'll also get a 1 on through here, right? So what does that mean for my result? It's always true. It's just always a 1, right? And so then our last option down here with the 1, 1 says, okay, I know that this can never be active. There's nothing that I can do with it. Absolutely nothing that I can do. So we don't have to consider this particular case. If Q is, let's see, if Q is high, then this guy's off. If Q is low, then this one will give us a 1. So what do we actually get here? We get the opposite of Q, Q not. Right? So we've got a lot of cases where we're just storing. We do have a 0 here. We also have a 1 here. We've also got a flip here as well. So what does this allow us to do, right? It allows us to not just set, right? If one of these is high, it acts in a similar fashion to our set and reset bits that we saw, right? If they both go high, we just toggle. It actually behaves exactly the same as our toggle if they're both high, right? And if they are both low, then we're basically in storage mode, right? So it's kind of a combination of our toggle as well as sort of an SR kind of functionality. This is called a JK flip-flop. That also has some other uses. We might see some practical applications of JK flip-flop in future classes. Are there any questions about that one? Questions? Let's see how we're doing here on time. I'll tell you what, I do have one more problem, but I do want to make sure to talk about the lab too. So let me talk about the lab first. If we have time, we can take a look at the last problem. So the lab. Let me just go ahead and, I guess, pull it up here real quick. It's been assigned today. It's due a week from today. It is a pretty short lab, right? So I do think that doing it in a week is very, very doable. However, I also think that you should start as soon as possible because, again, you are going to have to demo this lab. And if everybody comes in to demo the day that the lab is due and the GAs can't get to it, then my answer is going to be sorry. You had 7 days to demo this lab, right? So try and get it done early. Try to demo it early. You can do the entire lab basically without having to demo it. So there is a lot of work that you can do before the demo piece actually matters. I would say do as much as you can at home on your laptop with your partner before you demo, and just worry about the demo as the absolute last thing that you do. So what are you actually going to be doing? It's a very simple circuit that I'm asking you to implement here. It's a calculator, and I use that word very, very loosely because the only thing your calculator is going to be able to do is shift left, shift right, add 1, or subtract 1. That's it. That's all you're going to be able to do. But actually, if you think about it, right, if I keep adding 1 repeatedly, I can add to whatever value I want. Same thing for subtraction. And shifting left or right is basically equivalent to multiplication. So I can, with those 4 operations, get where I need to go, right? You probably recognize the shifting action from Lab 1. That is not a coincidence. You're actually going to build off of that solution to Lab 1. So you're going to take that schematic that you made in Lab 1, and you're actually going to incorporate it into your solution for this lab. I want you to do that. If you didn't complete Lab 1 for some reason, or you just really, really hate what you did for Lab 1 for some reason, I did go through an alternative implementation of Lab 1 in one of the course videos in VHDL. You're more than welcome to use that. However, for the vast majority of you, you did very well on Lab 1. I would say just stick with what you've got, unless you receive poor feedback from us. So you should incorporate that into your solution. There's instructions in here on exactly how to do that. You're actually going to be writing code this time, so you're not going to be creating any additional schematics. You're going to use the schematic that you already have, but you're not going to be creating any additional schematics for this particular assignment. So you need to figure out how to make all this stuff work, right? You've already got the shifter done. That's a big first step. You have to figure out how to do the increment and decrement, right? And you have to figure out how to take in this opcode. I need to know what operation I'm performing, right? I need to be able to choose what operation I'm performing. So you need to implement that. We're going to have a way to implement what operation is actually being performed. So, go read the lab write-up. I gave you step-by-step instructions on the whole deal. Just one other thing that I wanted to point out is we are going to be asking you to implement this on the FPGA for this particular lab. And every lab here on out is going to use these FPGAs. I know we haven't talked a lot about what these FPGAs are. That's coming very, very, very soon. I can give you kind of a quick rundown of what that means for you on this particular lab, right? You're going to take your VHDL code and you're actually going to convert it into a hardware implementation on this circuit board. The circuit boards are in the Brian 316 lab where TA office hours are. They can access those for you, right? And what it's going to allow you to do is there's a knob on here that you can spin around, and there's also some switches on here. Right? You can use the knob to select your input value. So any number that you want, right? You just spin the knob, so you get the value you want. You can use the switches to represent the opcode, right? If the switch is up, it's a 1. If it's down, it's a 0. And so your calculator will be able to work on this board. There's even a screen here, a little small screen that can show you what input is, what the output is. So you'll actually be able to sit there and change the opcode, right? And perform different operations and see those changes happen instantaneously on the hardware as you play around with it. So it should be a lot of fun, right? I know this is very simple. I'm trying to get you used to working with these boards. We are going to be working with these for the rest of the semester, though. So we'll do a lot more complicated stuff in future lab assignments, and talk a little bit more about what all you can do with these boards in future lab assignments as well. So let's see, is there anything that I forgot? I mean, a lot of it's the same. You have to write a test bench. Yeah, questions?
From lab 1, we encourage that it's easier for us to use the guidelines installed in the CSE computer rather than trying to be able installing it ourselves.
Sure.
For this and future labs, that we actually do install guidelines ourselves and set that up, or is it still perhaps easier for us?
I mean, that's a decision that's up to you to make. Xilinx is kind of a cookie program in general, so just to give you, some reference, I basically blew up my computer from scratch and started over again and had to reinstall Xilinx, and it took me a better part of a day to get it up and functioning with the FPGAs the way that I wanted to. I'd say for the demos, like when you're actually hooking up to the hardware and demoing your lab, you're going to use a lab computer no matter what. Not to say that you couldn't do it on your laptop if you really, really, really wanted to, but it's probably going to be more hassle than it's worth. For everything up until that point, right? If you're just doing the simulation with the test bench and all you're doing is working with code, that part I could actually see being worthwhile to install it on your laptop and use your own personal machine for that piece. But for the demo, I think, yeah, hands down, you're probably just going to use lab machines, which means you will have to copy your stuff over onto the lab machine at some point if you decide to start on your own laptop. Yeah.
I guess a follow-up question to that is that in lab 1, there was actually a time when we were running code when we set up a schematic on a test writing code on like a CSE computer in Earth Hour, and we kept getting a lot of unexplained errors, and then we were told that we just tried the same code, no changes made, and Ryan, whatever the TAs are in, and actually the code worked. I'm just wondering like if there's any like weirdness that would happen if we tried to do this even just on test bench laptops.
You know, it depends on the error. I ran the first lab on the CDC machines in Neubauer, as well as the Brian lab, as well as on my own laptop. I tried it in all 3 places, and I got it to work without any major modifications in all 3 cases. So they are all set up to work. If somebody's come in and done something weird on one of the lab machines, then it might not work. I can't, I just kind of have to take it on a case-by-case basis. But it should work on all of the available machines on campus. Okay. Yeah. Are there any other questions about that right now, about the lab assignments? So you can work with a partner. Part of this is going to be drawing up the schematic. I want to see a schematic for this. Actually, this is really important. This is actually perhaps the most important part of the lab. I want you to get some experience writing code too, right? But I want you to also get some experience drawing up circuit schematics. Right? And I'm going to expect you to use multiplexers. One thing that I noticed on the exam is that it seemed like people were going out of their way to not use multiplexers, which is, I didn't count off points for it directly, although it did make my life a little bit harder when it came to grading things. And I think actually probably made your lives a little bit harder than if you just use multiplexer when it's appropriate to do so. I'm going to be looking for that on the lab, and basically from here on out. If you go out of your way to avoid using multiplexer, I'm going to start taking points off for it. So you'll get some practice with that, and pay really close attention. The code that you write, the VHDL that you write, needs to match the circuit schematic that you turn in exactly. You're going to be checking for that. Right? It needs to match exactly. It needs to be exactly the same. Yes? That's all been done for you.
Awesome. And then, do you have to write our visual simulations in the HDL code, or could you just also write the simulation using schematic?
I want you to write code because we're going to be using code basically from here on out. Or we might be doing kind of a combo actually for some of them. We might do a schematic for a part and code for the rest, but we're going to be writing a lot more code from here on out. So I want you to do this one entirely in code. You'll be using the schematic that you created in the past lab, and then you're going to add code to that to make it all work together. Any other questions regarding the lab assignment? Yes?
We're not going to use schematics. We have to draw the circuit schematics. We're just going to like print out a new copy of our last schematics from lab 1.
Oh, well, that's a good question. You don't need to redraw your entire schematic from lab 1, right? Use a component. Use a component for that part. Here's my shifter. Here's my shifter. I have inputs over here, right? You can just refer back to the lab assignment for that. Drop a component in there to refer to everything that you did for lab 1. Don't re-implement that entire circuit. Make it a component. Yeah?
When we try to add 1 to 7 and subtract 1 to 0, what do you want us to do?
It should just overflow. It should just wrap around. We haven't actually gotten. We haven't actually gotten to proper arithmetic, proper binary.
7 plus 1 is easy. Because that's all here. What do you want us to do?
0 minus 1 is 7 in this class, at least for right now.
All right.
That will change later, right? But for right now, 0 minus 1 is 7, and we'll fix that. Actually, pretty soon here, we'll fix that particular scenario. Yeah.
On the side.
Yeah. Any other questions? We still have 5 minutes left, and there is still one question on this slide deck. I know you guys want to leave, so whatever, You're all grown up, so you can do whatever the hell you want. But if you want to stick around and talk about this last question, you can do that too. It's up to you. Right. I will stick around in case anybody has any questions about any of this other stuff, including the lab, including these questions, whatever you want. Yeah. Don't know what the application is called. It's like finding an equation out of it, right? So saying x plus b plus c equals c plus d. Yeah. I mean, really, I only care about what I could have added. Yeah.
Can we talk to you about our lab grade real quickly?
Sure. Yeah. What's up?
Okay, so we noticed last night when we got like we had a 100 on it,
Okay.
and we didn't realize that it's Blackboard.
Okay.
We had the TAs demo it, it was working perfectly. Can
Okay.
we just submit it and give us feedback?
Yeah. Why don't you shoot me an email and include the files on there, and I'll take a look at them and figure out what to do.
Awesome.
The answer is you can probably get some points back. I might just take a penalty off, or leave a penalty off. Or something
Okay.
like that.
Okay, we submit everything all the time.
Yeah.
Yeah, we
Yeah.
just honestly. do
No,
not
it's the
read
first
that
lab.
line.
I understand.
Yeah.
So
Okay.
we'll figure it out. Just shoot me an email, include the stuff, and
Awesome.
and I'll do a regrade.
Great, thank you.
Yep.
Thank you.
Hey, Professor Tripp.
Hey, what's up?
Just stopping by.
Yeah.
Yep.
How's oh, thanks for the exam grading, by the way. I'm almost done. So that's nice. Okay. Cool. How's the homework 2 going? Do you have any idea?
Oh, I finished my test.
Yeah.
So I think we're like more or less working
That's good. I know I've been leaning on you guys a lot lately, so I haven't been.
This will be like
too-
that last day of like, oh man, I guess now that we procrastinated long enough. Yeah. I was like, probably shouldn't have
Yeah. It'd be nice to have those in by like the end of the week or sooner. Like if I could hand them back on Thursday, that would be awesome.
Yeah, also like a reminder.
But if I don't get them, you know, I mean, I'm not going to go back too much. Have that exam.
Yeah.
So I understand that you guys aren't grading machines. At least not most of the time.
Only when they see it involved.
It does make me feel so much better to get that grading out of the way because it was kind of pounding up and I was getting
Yeah, it was like this string of creative,
Well, there's gonna be another one next week, so I want them in by Tuesday at that.
Yeah, they're just grading and we can actually
we'll
do
try to
them all.
have them by Thursday. I'll send a reminder.
Cool. Thanks,
So
man.
to recap for this lab 2, we don't need to like write out the schematic like in terms of all the like lines of stuff in a file. We didn't draw out the diagram, but we still have to make a test bench.
I want to see the diagram, and then you're gonna have to write the VHDL code that matches that circuit. So if I look at your code, right, and I take that code and I was to transform it into a circuit, it better look exactly the same as the circuit diagram that you draw and turn in.
I think I'm understanding it right. Which part of lab 1 constitutes the schematic?
Which part of Lab 1 constitutes the schematic?
As a test bench.
I don't want you to make the schematic file anymore, because that schematic is what was actually being tested. I don't want to test the schematic. I want to test code.
Oh, I see. So the schematic and the test bench, neither of you are code. We're actually writing code.
Well, the test bench is code. Like the test bench was code last time, and it's still code this time, right? But you didn't test it. The test bench was not being applied to code, it was being applied to a schematic. Now I want you to apply the test bench to some code.
Schematic.
Every single thing that you write in VHDL can be turned into a circuit. Everything. So really, when I enter in a schematic in Xilinx, right, I could also go in and enter code that does the exact thing.
So it's just 2 ways of doing the same thing. We're doing it differently.
Yep. Yep. Pretty much. Okay. You'll need to talk to Kelly. Hold on.
to go in and do that, adding hours, and then, I'm not sure how to do it. Just working to talk to you about that. Thanks for helping. Was it? I hope so. Probably. I know it's a little chaotic. Maybe I'll talk about it. reason, the new IKEA means Western streets are likely the new norm. That's on top of about 12 hundred and a half dozen new residential projects in July. To make way for more visitors, IKEA has paid for extra west turn lanes, signals intersections, and resurfaced